Transport infrastructure for Europe, the new bridge over the Danube between Bulgaria and Romania. In 2006, selected by the Bulgarian Ministry of Transport in an international bid, FCC Construction was awarded the design and construction of the Danube Bridge 2, as well as its accesses including 2 railway stations for passengers and goods. These constructions have been jointly financed by European funds and by the Bulgarian state. The bridge connects the towns of Vidin, Bulgaria, and Calafat, Romania, but its real importance goes far beyond that, as it joins the pan-European transport corridor by road and rail, which goes from Germany to Turkey, besides being the second bridge over the Danube in the more than 650 kilometers of the border between Romania and Bulgaria. The contract was signed in March 2007. The work began in November 2008 and finishing the construction at the end of 2012. On the Bulgarian bank, the 4-lane motorway and the railway tracks meet, the latter coming from a higher level. Joined on the bridge crossing into Romania, the road opens in the center for the railway track, and both continue at the same height, first over a non-navigable stretch of the river and after over the navigable channel. The bridge is 1,791 meters long, with a unique unsymmetrical deck with 2 exterior 4-lane roadways totaling 15 meters, 1 central railway platform of 6 meters, 2 pavements and 1 bicycle lane, which make a total of 31,35 meters in width. The motorway is designed for a speed of 100 kilometers per hour with a maximum slope of 4%. For the railway, however, the speed is 160 kilometers per hour and its maximum slope 1,25%. The bridge is divided into 3 distinct parts. The railway access bridge. It's 772 meters long, which comprises a span of 32 meters, 13 spans of 40 meters and 220 meters of transition between the railway structure and that of the bridge over the non-navigable river channel. Built in situ by means of a scaffolding truss, it's composed of a post-tensioning concrete deck with a transversal section in the shape of pi and a platform width of 8,6 meters with a constant thickness of 1,89 meters out of the transition area. The deck is held up by 13 double piers, whose shafts are circular reinforced concrete pile piers of 2 meters in diameter. The length of the piles varies between 35 and 61 meters. The bridge over the Danube in its non-navigable stretch. With a length of 646 meters, its deck is made up of a central caisson comprising precast segments of concrete 2,15 meters long, 4,5 meters thick and 10,9 meters wide, and exterior wings resting on struts every 4,3 meters. Mounted on each pier by the balanced cantilever system, they have a longitudinal pre-stressing within, which connects them, passing through the upper and lower slabs. The spans are 80 meters long, except for the first, which is 52 meters long. It's supported by 8 concrete piers in box sections and variable height of up to 20 meters, bounded in pyramidal pile caps of 15 by 15 by 4 meters and 6 or 7 piles of 2 meters in diameter, with lengths between 55 and 72 meters. Bridge over the Danube in the navigable channel. It's 745 meters long, spread over 3 central spans of 180 meters and 2 lateral ones of 124 and 115 meters respectively. It has 4 concrete pylon piers with a variable height between 39 and 45 meters, founded in pyramidal pile caps of 15 by 40 by 6 meters, which support in 24 piles of 2 meters in diameter and lengths between 61,5 and 80 meters. The deck is equal to the non-navigable stretch, also mounted in each pier by balanced cantilevers, but from the river and with segments much larger and heavier, 4,18 meters long and 250 tons in weight. Besides the internal longitudinal pre-stressing, due to the greater length of its spans, it requires an extra-dosed pre-stressing which comes from the upper slabs of the segments and is anchored to the pair of pylons 22 meters high in each pier. The piers have two longitudinal struts which, coming from the pile cap with an inclination over the horizontal of some 55 degrees, hold the deck being embedded in it and improving the function of the stays of the extra-dose system. For the protection against the impact of vessels, each pier has 38 precast concrete pieces of between 85 and 135 tons installed, joined to the pier by a pre-stressed grillage, and between them with reinforced concrete tie beams cast in situ. To carry out the building works, both for the bridge and the accesses, FCC built a machinery and equipment park 3 kilometers downriver from the bridge, with a total surface of 22 hectares. In it there was available, amongst other things, 5 segment fabrication lines with the necessary infrastructure for the production, distribution and cast-in place of the concrete, steam curing, steelwork base, manipulation and stockpiling of the production. There were also 2 prefabrication lines of defences for the pile caps of the piers of the navigable channel, 1 elephant crane of 250 tons capacity, other lines of secondary prefabrication for beams, piles, segment struts, etc., 1 tower crane, 2 concreting plants with a water heating and cooling system, 1 agglomerate plant, covered warehouses, 1 steam plant and another of compressed air, 2 aggregate crushing plants, 15 hectares of storage area and 1 cargo port with access to the river, provided with a gantry crane of 250 tons capacity. The segments have been built by matchcast segment system, which use each segment as a formwork for the next one, thus obtaining a perfect join between them. The geometry of each segment is variable in order to adapt the deck to the layout of the motorway. That requires a very rigorous topographic control of production with a tolerance of less than 1/10 of a millimeter. In the segments making, concrete of between 50 and 80 megapascals of resistance has been used, depending on the parts of the bridge. The foundation of the bridge over the Danube has been one of the main challenges of the construction, in the design as well as in its execution, due to the lack of full geotechnical information and the difficulty of positioning the piles in the river bed. To that must be added, besides, the great variation of the water level between the low watermark and the higher floods, which could reach up to 11 meters. For its final design, a detection of explosives or sunken boats was carried out in the area of influence, and another additional geotechnical campaign in the whole length of the bridge, with drillings of up to 100 meters depth in sight of each of the piers of the navigable channel. The piles were drilled using bentonite muds and with permanent steel casing of 12 millimeter thickness, with a variable length of between 12 and 35 meters. Once the excavation was finished, the recirculation and cleaning of the bentonite by means of an airlift system was begun, a process which lasted between 2 and 3 hours, depending on the length of the piles. Later, the reinforcement was introduced in 12-meter sections, joined by welding and a final airlift before concreting. The foundation of the piers of the non-navigable channel was made from the shelter of a circular enclosure of sheet piles of 25 meters in diameter. For that, a peninsula was previously built with an access road to all the piers. The piles in the navigable channel, which are the deepest ones, up to 80 meters, were carried out with teams on pontoons, which made it very difficult for the maneuvering performance as well as the on-site layout. One of the great achievements of this stage was developing concrete formulas with 450 kilos of cement and a workability of 3 to 4 hours, with the purpose of arriving in optimum conditions to the spill area, and cuts in the piles were avoided. The ones on the non-navigable channel, with a volume of 640 cubic meters of concrete, were carried out in a single concreting. Those of the navigable channel, with a volume of 2,350 cubic meters of concrete, were carried out in 2 phases. These pile caps are longitudinal and transversely pre-stressed for the fixing of the defences against the impact of boats, which were later installed. The defences came from the nearby park of prefabricated items transported from there by river on pontoons, and they were hoisted with equipment of heavy lifting attached to a metallic gantry designed for it. Once hoisted, the defence was pre-stressed through the pile cap to fix it in its final position, later bracing all of them with 3 levels of concrete tie beams, casted in situ, making the whole system a resistant unit against the impact of boats. The piers of the non-navigable channel are finished in a filled-in head, on which the deck is supported by means of spherical supports and a longitudinal guide. In the piers of the navigable channel, however, the deck is embedded in them with a second phase concreting between deck and pier. From the head of the piers of the navigable channel spring 2 massive pylons 22 meters high of variable geometry and strongly reinforced, where the saddle will be housed, the pre-stressed element which will support the stays of the extra dose system developed by BBR for the construction. The saddle consists of curved galvanized metal ducts placed in the interior of the pylons, which are pre-stressed before anchoring the extra dose stays on them. What is a novelty and absolutely revolutionary about this system is that as the tubes are pre-stressed when the stays of the extra dosing pull in the opposite direction, the habitual oscillations of tension in the cables won't be produced, and this is essential in such a difficult element to substitute. The joining of the struts with the deck is carried out by means of a diaphragm concreted in situ, complex for the necessary precision in the mounting of the formwork as well as the steel frameworks, which is full of sleeves. For the execution of the piers, FCC has had 4 tower cranes of 70 meters of boom from its machinery park. In the non-navigable channel, the segments arrived by road and were placed on the deck at the end of a launching girder which places them in balanced cantilevers on each pier. 300 units were placed in this way with a maximum weight of 100 tons. The segments were prefabricated with some interior bulks beside the webs, which were used to join each other provisionally with pre-stressed bars. Once the segments corresponding to each pier were placed, the complete stretch was replaced by means of 4 hydraulic jacks housed in the head of the pier. After each stretch was joined to the previous one, executing a closing segment in situ, and then the definitive internal pre-stressing was carried out. The exterior wings of the deck were also executed in situ by means of sliding gantries which were supported on the central caisson. Due to the width of the deck, this was carried out in 2 phases, the first from the central caisson up to the connection of the struts to the deck, and the second from the previous edge up to the deck's extreme. In the navigable channel, the realization of the deck needed, due to its singularity and complexity, a great amount of previous work of engineering in the development of the hoisting equipments and the execution procedures, as well as in the development and adaptation of the pre-stressing and extra dosing systems. In this case, the segments, which already bring part of the wings from the factory, arrived by river, loaded in a pontoon, and were placed beside the pier. The first 10 were hoisted by means of a system composed of a metallic structure anchored to the pylons and a winch with rails which ran along it. The first 2 were placed on decks replacing jacks, and they were braced to the head of the pier with a vertical pre-stressing. Once the remaining 8 were placed, the set were replaced again by means of 4 jacks, each of 1,700 tons. After, the hoisting structure of the segments was dismounted and the deck was joined to the struts and the head of the pier, making all of them, pier, struts and deck, working monolithically. Following, a mobile segment hoist crane was mounted which, circulating on the already assembled segments, would be responsible for hoisting the remaining segments of the stretch. The process of hoisting a pair of segments took 16 hours, but the complete installation along with the 4 stays of the extra dosing which would go with them took between 3 and 4 days, working 24 hours, depending on the length of the stay and of the number of strands, and consisted in, with the mobile crane fixed to one of the sides, the segment on that side was hoisted. A resin was applied to the facing of the previously placed segment, and when both were in contact, they were provisionally joined by means of pre-stressed bars. The mobile crane was moved along the deck and fixed on the other side. The segment of that side was hoisted, joining it to the previous one in the same way. The definitive pre-stressing of the segments was threaded and pre-stressed through the interior of the deck. It was concreted in situ using independent deck wing gantries, which remained from the wings of the previous segments. From the upper part of the deck, the stays of the extra dosing were hoisted, fixing them in the pylon saddle and inserting them into the deck. When the necessary resistance of the concrete was reached, they were pre-stressed with a single strand jack from the upper slab of the anchoring segment. Once the installation of the 42 segments of the stretch was finished, its joining with the previous stretch was begun. For that, a prefabricated segment, 3,18 meters long, was suspended from the mobile crane between both stretches, and 2 closing segments of 50 centimeters were executed in situ, in such a way that they fitted perfectly on the closing. After the provisional joining with pre-stressed bars, they were definitively joined to the deck by means of the internal continuity pre-stressing. In the area near the Romanian bank, the central caisson was executed in situ, supported by a falsework bent and 2 provisional piers. This stretch, of 52 meters in length, leant on a system of jacks for its later descent, so that the coupling with the deck of prefabricated segments could take place. The wings of the deck in this area were carried out with sliding gantries on the central caisson. Once the deck was completed, the finishing works and the assembly of the installations of the bridge were carried out, as well as the layout of the railroad on ballast, using guard rails in its whole length. One of the most complex elements in the design of the bridge, due to the movements, have been the expansion joints in the abutments, as much those of the road as of the railway tracks, these last being the most difficult due to the parameters required for the circulation of the trains at 160 kilometers per hour. That of the Bulgarian side especially, besides being one of the biggest in the world, has the added complication of being on a bend. With this magnificent bridge for its dimensions as well as for its functionality, strength, quality and aesthetics, which crosses a no less magnificent river and one of the main natural obstacles of Central Europe, FCC Construction has given continuity to a strategic transport route of more than 2,000 kilometers, which goes from Dresden in Germany up to Istanbul in Turkey. The bridge has been executed with FCC Construction's own means in the prefabrication of elements as in the assembly system, which has meant reaching speeds 3 or 4 times faster than conventional methods, besides a completion of great quality, ensuring the security of the workers at all times. It's an impressive work of engineering which has shown once again that FCC Construction can overcome any challenge which presents itself, making life more comfortable for those who have trusted in it, thanks to the preparation and dedication of its construction workforce, as well as the unquestionable quality and permanent support of its technical services.